So today we're going to look at the electrocyclic ring closure of 1,3,5-hexatriene. What we will learn, what the reaction does, why and how it does what it does, and what happens to the stereochem. So what does an 80s flashback have to do with the reaction? Well, the electrons spin around, and the ends will rotate. The ends I'm talking about are these ones in the circle, and then a bond forms between those two carbons. The why is pretty easy, as per usual. It's about stability. The how it does what it does is a little more interesting. So to start, look at the orbitals that are formed by the pi bonds. So as you can see, there are 6 different orbital configurations, as shown on the left, in order of increasing energy. So in the ground state, you can see that it's in the 3rd one, and you'll notice that it is symmetric about the center. If you promote an electron with light, you'll see that it moves up to the next one, and it is antisymmetric about the center. It applies mainly to the end, where the two ends where they're going to come together. That is where the orbitals matter. As you can see on the left, we see the compound in its ground state. So you'll see the two orbitals right at the end of the molecule are the same, in the same phase and lined up. And if you do it photochemically, you'll see that they're not lined up, they're opposite. So in order for a bond to form between them, these orbitals have to rotate together, and the way in which they do that depends on which configuration the orbitals are in. So if you do this thermally, they are aligned, as you can see in the left picture, and in order to form the bond and have two orbitals of the same phase overlap, they must rotate in opposite directions. This is called disrotatory. If you do the reaction photochemically, you've promoted an electron, and now you are in a higher energy state, and you'll see that in order to get overlap, this time you have to rotate in the same direction, so we call this conrotatory. Here's a balloon demonstration. As you can see, when done thermally, the two black balloons must rotate in opposite fashions in order to come together. Now you'll see photochemically that in order to get orbital overlap, you have to rotate in the same direction. There's easy rules to know whether the ends rotate in a con or disrotatory fashion. If there are an odd number of pi bonds and it is done thermally, it will be disrotatory. Now this statement is true all the time, and since each of the options or components have only 2 possibilities, you can negate any 2 and it still remains true. So if you have an odd number of pi bonds and you do it photochemically, the ends will conrotatory. So what happens to stereochemistry? Well, it's just one molecule in the reaction. There's nothing coming in or nothing leaving. So what's attached stays attached. So in order to know whether your substituents go up or down or cis-trans, you have to look at the rotation, which, as we've seen, depends on the reaction conditions. So in this picture, it's done thermally, and you can see that the 2 methyl groups on the outsides will both go up, since they're both rotating in opposite directions. And here are more balloons to illustrate that. As you can see, the sticks on the outside represent the methyl groups, and of course there are hydrogens on the other side, so they too will rotate. But if you rotate the orbitals together to match the same phase, you can see that the sticks both go up. Therefore, you would get the the cis product. Now, if you do the reaction photochemically, you'll see that in order to come together, the two sticks will go opposite to one another, so you'll get the trans product. So hopefully now you are all experts at the ring closing of 1 through 5 hexatriene.